Hey everyone, welcome back to Calculus 3. This is going to be lecture 6 of the course. The previous 5 sections of the previous 5 lectures, we have studied, kind of been brought up to speed on the vector topics that are going to be necessary for vector calculus and calculus 3D space. This final section is going to bring us the necessary understanding of surfaces in space and how to think about those. And then once we're through this lecture, given the 5 that we've gone through already, and this one, we'll be ready to jump into vector valued functions and ultimately move into tangent vectors, normal vectors, and start talking about differentiation, integration of these kinds of functions. So this has all been kind of a preface to Calc 3 a little bit, because I mean the reality is when you first take Calculus 3, it's unlikely that you've had a whole lot of three-dimensional mathematics. You might have taken a geometry course which dealt with 3D math a bit, but most people haven't seen a lot of three-dimensional math up to this point. So this will be the last section of that kind of recap or prep work or preface to Calc 3. So let's go ahead and jump into it. And so we'll call this section 1.6, surfaces in space. Okay. And so up to this point, we have seen some surfaces in space, right? So we've seen already spheres, right? So spheres, like basically take a circle in 2D space and rotate it, and you get a sphere, right? And we saw that the equation for a sphere was x minus x0 squared plus y minus y0 squared plus z minus z0 squared equals r squared. Now here, x0, y0, z0 is the center of the sphere, and r squared is the radius of the sphere. Okay, so we saw that. We've seen those types of three-dimensional shapes. We've also just got done talking about planes. Okay, and so planes can be represented using the equation ax plus by plus cz plus d equals 0. And in this case, the a, b, and c are the three coordinates of the direction vector of the normal of a vector normal to the plane. Right, so we've seen these equations. So far these are what we've seen, and really the point of this section is to kind of expand our repertoire a bit into a few other shapes. I mean, and we're not obviously going to get into every shape, but just a few of the common shapes that have a role to play in what's to come in Calc 3. Okay, so the next one to look at here is the cylindrical surfaces. So cylindrical surfaces. Okay, so you can kind of think of this as, you can imagine what this would look like. Say we've got something like this, right? And then kind of goes like that. And maybe you've got your y-axis here, and you've got your x-axis coming out here, and then at the top you've got your z-axis. Okay, and so you can see where these would kind of come together here, right? Okay, and so for a cylindrical surface like this, the way to kind of think about it is you can just imagine a cylinder as being just a vertical line in space moving around a circle, right? So we can think of a cylinder in space as just a vertical line, okay, a vertical line moving around a circle. Okay, it's like in the case of the most simplistic kind of cylinder, something like this. And in those instances, so you've got some kind of a circle down here, and let's imagine this circle lies in the plane, the XY plane. So this circle has an equation, right? So this circle has an equation. And the equation is just x squared. If it's in the xy plane, it's x squared plus y squared equals a squared. Okay. And in this example, when you have a cylinder built in this way, just the vertical lines that are rotated around a circle, this circle is called a generating curve. Okay. Okay, so the circle is called the generating curve. Okay, so that's kind of the setup. Now the way to think about it is, yes, you've got vertical lines. Now, with a cylindrical object like this, the assumption is that the vertical lines can go on forever. Now, it's possible to truncate them if you like, but you want to imagine these as kind of just going in either direction forever. And then what you do is you take that line and you rotate it around an axis, or it doesn't have to necessarily be centered at the origin like this, but you want to rotate it around whatever the generating curve is that's relevant to the shape. Okay, so in this example, the generating curve is a circle of radius a that lies in the xy plane. Okay, and you take this line and you rotate it around this circle. Okay. Now, in this drawing, the assumption is that the vertical lines, we say the word vertical, and we know what that means. It's coming directly off of the plane. But in general, whatever plane the generating curve lies in, the vertical lines are perpendicular to that plane. Okay, so in this case, these vertical lines are parallel to the z-axis, which is perpendicular, of course, to the xy plane. Okay. All right, so let's define this. Let's kind of sum this up a little bit nicer. There's a lot of concepts here. Let's summarize this a little bit more in a nice definition. Okay. So we'll let C be a curve in a plane. Okay, let C be a curve in a plane, and let's cut this off here, and let L, okay, be a line not in a parallel plane. Okay, so this L basically is perpendicular to the plane that C lies in. Okay. Then the set of all lines parallel to L the set of all lines parallel to L and intersecting C is called a cylinder. Okay? Right, so pause for a second and let's reread that and try to absorb this. So C is a curve in a plane, right? And L is a line not in a parallel plane to C. Okay, so the way to think about that is you've got, take the simplest example where the line is literally perpendicular to the plane in which C lives. Okay, then a cylinder is the set of all such parallel lines. Right, so you can imagine parallel lines, all lines parallel to what we have here, this initial line, that intersect this generating curve. Right, the generating curve in this example being a circle. Right, the set of all such lines is what we call the cylinder. Okay, so a cylinder in space is basically a collection of parallel lines, right, that are arranged according to some generating curve. That sort of definition, obviously not the same as, but has a lot of similarities to the definition of a circle. And for in the plane, we say a circle in the plane is the set of all points equidistant from another given point, right? So this is a similar kind of idea. It's a shape that's sort of defined in set theoretic terms, right, as this collection of parallel lines that intersect this generating curve. Okay, a little more detail on this. Okay, so C, we already said this, but let's write it down. C is called the generating curve. Generating curve. Okay. Another term that's used is the directrix. The directrix of the cylinder. So C is called the generating curve of the cylinder. And the parallel lines, they have a name as well. They are called rulings. Okay, rulings. Okay, so you've got this generating curve, and you've got all the set of all such vertical lines, aka rulings, that intersect the curve that are parallel to this given line. That's called that. They make up what's called a cylinder. All right. So that's the formal definition of a cylinder. Now, the generating curve doesn't have to be a circle. It can be any shape you like, and it's still technically a cylinder. Okay, a cylinder in space. So we'll get into a few examples in a second, and we'll see what this looks like. But let's take a little bit more time and talk about what. Let's talk about this in just a little more detail. Okay, so in the example we were just looking at, so in the previous example, the generating curve was a circle. Okay, and the equation there is x squared plus y squared equals a squared, where a is the radius of the circle. Okay. So to generate a cylinder, one thing to note is that any one of the rulings can be found by fixing x and y and letting z vary. Okay. So any one of the rulings can be found by what? Fixing x and y and letting z vary. Okay, so basically you just find a spot on the circle, and the rulings are just all of the fixed xy coordinates and letting z vary. Right, so for example, if this is our generating curve here, maybe this point right here is 1, so it's in the xy plane, so this is maybe 1, 2, 0. Okay, then the ruling is just going to be the vertical extension of that point. So maybe up here you got another point, 1, 2, 5, and then in between, of course, you'd have 1, 2, 3, right, etc. Right, and down below maybe it's 1, 2, negative 5, right, down here. Right, so this is of course where the z-axis is, and this would be negative z in this direction, right? Right, so these rulings are just basically you fix x and y and you let z vary, and you've got the rulings. Okay, so the value of z is totally arbitrary, right? And the equation of the cylinder, given that the value of z is totally arbitrary, the equation of the cylinder is really just the equation of the generating curve. Okay, so because the value of z, and I should say in this case, is totally arbitrary, the equation of the cylinder is just the equation of the generating curve. So in this case, it's x squared plus y squared equals a squared. All right. Now, this is only true if the rulings are perpendicular to the generating curve and the generating curve lives in one of the planes. In our example, the xy plane. Right now, if your cylinder deviates from this, then you have to potentially rethink a little bit of what the equation is. Okay, but for our purposes, we're gonna roll with these assumptions that the generating curve lies in one of the planes and the rulings are perpendicular to the generating curve, meaning that the value where you are on the ruling is totally arbitrary and not part of the equation. Okay. All right. So I know this can be a little bit of a challenging section, but let's do an example and see if we can make this a little bit more straightforward. Okay. So let's do an example. Let's sketch the surface. Let's sketch the surface represented by z equals y squared. Okay, so this will be a cylinder. Now, let's start with our coordinate plane. Okay, and so we'll just kind of draw this in the standard way here. Sometimes it's better to spin it. Sometimes this works fine. I usually just start with this. Okay, so you've got your x, y, z coordinates. Now this is, you notice the equation is z equals y squared. Right, so the fact that z and y are included in the expression but x is not means that this generating curve, this z equals y squared generating curve, lives in the zy plane. Okay, so this generating curve lives in the zy plane. Okay. And so we could easily sketch this. So this is basically equivalent to what we're used to looking at in the xy plane as y equals x squared, right? But here instead, the height of the curve is on the z-axis, and the domain, of course, is the y-axis. So this is going to basically look like this. It's going to come up like this, and it's going to do the same thing over here. It's just a parabola, isn't it? Okay. This is the familiar parabola. Now, this is just the generating curve, right? So we're told that this is a surface represented by this equation. And so we can kind of imagine the rulings here that would run perpendicular to the zy plane, namely in the direction of the x-axis, right? And so they would come down like this, and then they would be underneath here, right? Always remaining parallel to this x-axis. It's a little bit tricky to draw these things, but this kind of gives you a sense for it. What visuals like this could really benefit from are colors, more colors instead of just black and white. But that's the basic sketch, right? So you can imagine this is just a curve in space. You draw a parabola on the xy plane, and then just make the surface run perpendicular to that plane, and i.e. parallel to the x-axis. Okay, the rulings would be parallel to the x-axis. Okay, so that one is hopefully helpful. Okay, so you can see how you basically just need to plot this function and then draw the rulings perpendicular to whatever plane this generating curve happens to be in. Okay, Very good. Let's do another example. Kind of like that one, but let's sketch the surface represented by, in this case, we'll say z equals sine of x. Okay, and we'll just say 0 less than or equal to x less than or equal to 2 pi. Okay, and so for this one, I'm going to kind of twist my visual a little bit here. I think this will be a good idea. So we'll go like this. So here's my z-axis. Here's my x-axis, and then we'll make the y kind of go like this. All right, maybe this wasn't the best idea. We'll see. So this is just the sine function along the x-axis, right? Right. So it kind of would probably look like this. Maybe go like this. We'll say, okay. Right. So that's what the sine function looks like. Now, what are the rulings going to be doing? Well, this will be hard to see, but they're going to run. Ooh, really hard to see. Sorry. They're going to run parallel to the y-axis, perpendicular to the xz plane, right? So they're going to be running along it like this. Okay, so you can imagine this surface that kind of extends, basically runs parallel to the y-axis, and then cuts perpendicular into the yz axis, and it's got this very distinct sine curvature to it. It's based on the generating function z equals sine x. Okay. All right. So again, a little bit tricky to visualize, but I think you guys can get the picture somewhat, right? Just use your imaginations here. Okay, so those are cylindrical surfaces, right? So just kind of to recap, cylindrical surfaces are based on a generating curve, and the surface is built using rulings that run perpendicular to the plane in which the generating curve lives. Okay? All right. Perfect. So that is kind of the third basic type of surface that we'll need, these cylindrical surfaces. Let's talk about the next type, right? And the next type is kind of a family. Okay, so the fourth basic type of surface is called a quadric surface. Okay, so the quadric surfaces. Now, the best way to think about quadric surfaces is that they're basically kind of like the 3D analogs of the familiar conic sections. So these are like 3D analogs of conic sections. And so remember the conic sections, you've got hyperbole, ellipse, circles, that kind of stuff. And so these are like 3D analogs of those two-dimensional shapes that we're used to looking at. Okay. And so we'll kind of talk through these, and probably kind of keep it high level. These are pretty tricky to draw, but the equations that are associated with these three-dimensional shapes are going to be used a lot in calculus. So I want people to be exposed to them and have at least some sense for what these represent as we get into the later calc topics. Okay, so in general, okay, the equation of a quadric surface. In general, the equation of a quadric surface is a second degree equation of the form. Okay, the form, this is going to seem ridiculous, but not, they don't always look like this. They're not always this long, but they could have any of these sort of terms. So ax squared plus by squared plus cz squared, okay, plus dxy plus exz plus fyz plus gx plus hy plus iz plus j equals 0. Okay, so any of these terms can be included in a quadric surface. We'll look at just kind of the main ones here, which will mostly consist of these guys here and these guys down here. All right, so let's just talk we'll kind of go through these in order, and I'll try to draw a picture of each of them, and I'll definitely give you the equation and some notes on how to think about the equation. Okay, so the first one is what's called an ellipsoid. Okay, the ellipsoid is, so let's say you've got, basically it's, if you draw an ellipse this direction, you draw an ellipse the other direction, it's where they intersect. Okay, and you're going to get a surface, kind of a rounded surface that is elliptical in both on the horizontal plane through the center, and also on the vertical plane through the center. Right. So the best I can kind of do is draw it like this, and this is not very helpful, but this is a tricky one actually to draw. So this is just called the ellipsoid, and the equation of an ellipsoid is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Okay, and the surface, this guy here, this surface is technically going to be a sphere if the denominators are all the same. Right, so this is a sphere if a equals b equals c, and that's obviously non-zero. Right, because you can imagine if this has all the same denominators, you can multiply through by that, and then you're going to be looking at your radius on the other side there. Okay. So that's the first one. It's called an ellipsoid. Probably the hardest one to draw. It just looks like a little bit like a blob in the way that I've drawn it here, but just imagine it's rounded, right? It has a top and a bottom and a side, and it's got some curvature to it all the way around. Okay, so the next one is called an elliptic cone. This is an elliptic cone. Now the way to think about this one is it kind of has like a top like this, right? And then it comes down, and it comes down over here as well, and it's going to have a bottom as well. Kind of like that. Okay. And so you can imagine your z-axis coming up the top here, and then maybe you've got your y-axis here and your x-axis here. Okay. And now obviously this is in 3D space, so there's some curvature to it, which you can kind of see here. Okay, this is an elliptic cone, and the equation of an object like this would look like x squared over a squared plus y squared over b squared minus z squared over c squared, and that needs to be equal to 0, right? So when all of the constants have dropped out to 0, you have an elliptic cone that looks like this. Now, something important to note here is that the axis of symmetry, right, this z-axis in this case, I think it's just mostly referred to as the axis of the cone. It's not the axis of symmetry necessarily, although there is symmetry here. The axis is going to correspond to the variable whose coefficient is negative. So here you see the negative is here. So the axis corresponds to the variable whose coefficient is negative. Okay, so that's the elliptic cone. All right, we've all kind of seen this shape. This is not unfamiliar. Okay, very good. Next up would be a couple of different takes on the hyperbola. So the first one is called the hyperboloid of one sheet. Now what that means we'll see in a second, right? So hyperboloid of one sheet. The equation of this is going to be x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Now, real similar to the elliptic cone, right? The elliptic cone was basically exactly the same on this side, but then on the other side, the elliptic cone was set equal to 0. So here you've got the other side equals 1. All right, now what does this look like? Well, kind of like elliptic cone, it has kind of a top, but then it comes down and does this instead of crossing over at the center. Right, so it's got kind of this, looks a bit more like this. All right, and again, it has some curvature here. Okay, and again, coming out the top, you've got your z-axis, and then you've got your y-axis, and then you've got your x-axis, right? Just like so. Okay, so you can see where these would sort of sync up here. And that comes out of the middle there. So that is the hyperboloid of one sheet. And again, the axis is represented by the variable whose coefficient is negative. All right, so that's where the axis is going to be based on that variable. So what's the difference between this and the next one, which is called a hyperboloid of two sheets? Well, hyperboloid of two sheets looks real similar. What you can imagine is that this central region here is going to kind of close off, and it's going to, and kind of the surface is going to sort of pull back on itself, right? So the hyperboloid of two sheets looks like this on top, but then it kind of comes down and closes off, right? But then you do have this corresponding lower section. It looks a bit like that. Okay, and you've got kind of the opening on the back side there. All right, so here's your z-axis, and then your y-axis is just right here, and your x-axis is, of course, right there. All right, so again, these are rounded. And so that's the hyperboloid of two sheets. One sheet. So you can imagine this thing kind of either stretching at the top and pinching at the bottom. And if you did that, you would eventually it would pinch off, and you would have kind of this two-piece hyperboloid. So the one sheet versus two sheet, of course, this is all one solid surface, or well, one continuous surface. This is two separate surfaces. Okay. In the case of the hyperboloid of two sheets, it's similar to what we saw before, but it looks like this. Here's the equation. It's z squared over c squared minus x squared over a squared minus y squared over b squared equals 1. Okay, so the equation is different. Here you had z as negative, and the other two were positive. And here you have z as positive, and the other two are negative. Right? And so the axis is going to correspond to the variable with the positive coefficient in the case of the two-sheet hyperboloid. Okay? Very good. Very good. So we're kind of tearing through these. Again, I mean, nobody expecting anyone to remember these or memorize these, but the general idea here is just to create familiarity with these shapes. Okay. Next up is the elliptic paraboloid. Okay, so the elliptic paraboloid has an equation of z equals x squared over a squared plus y squared over b squared. Okay, and what does it look like? Well, it's kind of like the previous. It's kind of like the hyperboloid of two sheets on the top here, but it's restricted to just the top. Right, so it kind of goes down like this, goes up like that, and that's it. So this would be your y-axis. Your x-axis would be naturally here, and your z-axis would be coming out of the top of the thing. Okay, so that would be the elliptic paraboloid. Okay, and here the axis is going to be represented by the variable that is a first degree variable. Right, so raised to the first power. The x and y in this case are second degree. The z is the first degree variable, so that's where the axis is going to reside along that direction. Okay, very good. And then the last one of this type is the hardest to draw by far, I'd say, and that's the hyperbolic paraboloid. So we just looked at the elliptic paraboloid. What about the hyperbolic paraboloid? Okay, so what does that one look like? Well, I'll start by trying to draw. So you've got some kind of a curve like this, okay, and then you've got kind of a saddle situation like this, and then the same thing on the back side. Okay, so you can kind of see there's like this curvature here, right, and then of course on the back side as well. And you can imagine your z-axis coming out of the top here, and then you've got maybe your y-axis extending like this, and then along the top here you'll have your x-axis. Okay, and so this is sometimes referred to as a saddle shape, but this is also known as the hyperbolic paraboloid. What does this equation look like? Well, it's kind of similar to the elliptic paraboloid, except you're going to flip some of the signs here. So z equals y squared over b squared minus x squared over a squared. Right, and again, the axis will be based on the single power. Right, in this case, the axis comes out the top, but then also the orientation of the saddle or the hyperbolic paraboloid will be determined by these guys here. So notice the y variable has a positive coefficient, and that's the piece that's kind of coming out the edge, the sort of side of the saddle, and the x axis is the one that kind of goes over the top. Right, sort of like you imagine if this looks like kind of like a slide, like you could slide down this side. The slide part of the saddle is going to correspond to the variable with the negative coefficient. All right. So these are tricky, right? These are real tricky. They're difficult to draw as well, obviously, and they're also hard to sort of sort out, right? But in general, kind of the key here is, to classify a quartic surface like this, you want to mostly begin by writing the surface in standard form, and then determining from that like what kind of a quartic surface is it, and then you can determine some of the traces. Where the traces lie, and you can kind of sketch it that way as well, right? Etc. So let's do an example of this. I'm kind of trying to figure out, given an equation, what sort of quartic surface we're looking at. and then try to kind of sketch it. Okay, so let's try an example here. So we want to classify and sketch. We want to classify and sketch the surface given by, and so it'll be 4x squared minus 3y squared plus 12z squared plus 12 equals 0. Okay, so you got something that looks like this. Okay, and so we're told that this is a surface, and this is the equation that represents it. So let's try to put this into standard form. So remember, all of the cortex surfaces have a 1 as the coefficient to on the variables. And so what we can basically do is divide this all down, right? And let's divide it down by negative 12. Okay, and so we would have 4x squared over negative 12 plus negative 3y squared over negative 12 plus 12z squared over negative 12 plus 12 over negative 12 equals 0. And why do we divide down by negative 12? Well, we want to turn this into a negative 1 so that when it moves to the other side, it's positive 1. And so what do we get here? We get x squared over negative 3 plus y squared over 4 plus z squared over negative 1 equals 1. Okay. And so a big part of determining what sort of shape we're dealing with, it has to do with these signs. So let's move the signs up and put them in the appropriate spot here. So this would be negative x squared over 3 plus y squared over 4 minus z squared. That's going to, we'll put it over 1 equals 1, right? And so this would probably be best written as y squared over 4 minus x squared over 3 minus z squared over 1 equals 1. And now what does this equation look like? What does this one look like? So this is a hyperboloid of 2 sheets. You can just kind of reference your notes on this, and you'll recall this is of the form. Okay, this is of the form z squared over c squared minus x squared over a squared minus y squared over b squared equals 1. The only difference here is that in the general case that we just looked at, the positive term was the z term. In ours, the positive term is the y term. Okay, so this is, but it has the same form, right? This is the hyperboloid of 2 sheets. Right, so that's the form that this is going to take. Okay, now the axis is the y-axis. Okay, so what is this guy going to look like? Well, without getting into too much detail, we'll just try to sketch it. All right, so you've got your y-axis, your x-axis, and your z-axis. So the axis of this hyperboloid is going to be the y-axis. So that means it's going to open like this. Right? And it's a 2-sheet hyperboloid, so it's going to come down and then come back up like that. And then it's going to do that over here as well, isn't it? Right? It's going to kind of do the same thing. It's important to remember these are going to be symmetric. Right? So it'll kind of look like that. All right. So that's what this particular surface is going to look like, right? And the equation in standard form is y squared over 4 minus x squared over 3 minus z squared over 1 equals 1. All right. Very good. Very good. Now there's more to this, but I think I'll kind of leave it at that. knowing that, you know, we'll come back to these in the future, and we can fill in any gaps that we need, you know, as we go through it. So, but the final kind of surface that we want to talk about in this section is what's called the surface of revolution. The surface of revolution. Now, we have seen this before, right? If you've taken Calculus 2, for example, you will recall surfaces of revolution, and what we had to deal with them at, you know, in that section. What we were trying to do is find the surface area using shell methods and washer methods for surfaces of revolution. And also volume. We were looking at volume as well. And so we've seen these before. A sort of characteristic surface of revolution might look like this. Right, maybe it comes down like this. Okay, and then it looks like that. Okay, and so this would be like the z-axis here, we'll say. Okay, and then let's just put the y-axis down here and the x-axis down here as well. Just keep them out of the picture. Keep it simple. Okay. Now, what you may recall was super important about the surfaces of revolution when we were discussing that in Calculus 2 was the radius function. Okay, the radius function. And the radius function is what told you, so there's an axis of revolution, in this case the z-axis, and you can imagine a function that runs along that axis, right? In this case it'll be a function of z, which tells you how far away from that axis of revolution you happen to be. And then the whole way this worked was you had this radius function, and then you just want to spin that around the axis of revolution. Okay. Right, and so it's helpful to kind of imagine some of the various points on here, right? So this point over here would be the point what? It would be the point 0, r of z, and then how high is it in the 3D space? It's z. So it's 0 on the x-axis, r of z on the y-axis, right? It's over here. Right, it's up, I guess it would be like right about here. Okay. And it is z up, right? Okay, so x, y, z. Okay, so it's r, z on the y. So this is your x, this is your y, and this is your z, of course. All right. Right, and so to find the equation of this type of surface, you really do need to begin with the graph of the radius function. Right, so in this case, the radius function is y equals r of z. Okay, in this case, the radius function, you would say, is in the yz plane as well, right? Okay, right, so really the radius function is this line. Okay, which is obviously in the yz plane. You can see x is 0 here. Okay, and so again, kind of reiterate, right? You have this radius function in the yz plane. We then want to rotate the graph of this radius function about the z-axis, and it's going to form a surface of revolution. Right? So it's if you were to rotate it around, right, around this axis here, you're going to get some surface. It's going to be spun out by this curve here. Okay. Now, it's important to notice that also, like the trace of the surface in the plane where z is equal to z0, it's just going to be a circle, right? So any of the traces in the plane z equals z0 is going to be just a circle, and specifically a circle whose radius is rz0, right? So let's write that down. The trace of the surface, okay, in the plane z equals z0 is a circle. Okay, it's a circle, and specifically a circle whose radius is whatever r of z0 happens to be. Right, r being the radius function. Okay, so the circle is gonna, the trace of the surface in the plane z equals z0 is a circle whose radius is r of z0 and whose equation is, well, it's a circle, right? So the equation is going to be x squared plus y squared equals the radius squared, and so the radius squared in this case is going to be r of z0. Okay. Hopefully this is clear, this z equals z0 plane. I want to make sure that's clear. So let's imagine this is z0, right? Then there's a plane that is defined here, right? Right, and this circle here happens to be in that plane. Okay, so we would call this guy right here, this would be the plane of z equals z0. Whatever z, and I say z0, z naught, whatever this fixed value of z happens to be. Right, and the whole idea is I can move this plane up and down, and wherever z naught happens to be, there's going to be a circle there who's defined by this equation, right? Because obviously the radius here will vary depending on the value of z naught. And so if the plane goes down, you'll have some other z naught. You'll have, this point will change, right? It'll be 0, r of, and that should be z naught, r of z naught, comma, well, we'll put 1, r of z1, and z1 we'll say, right? So the plane can move up and down here. Okay. Is that, hopefully that's coming across. You have to use your visualization skills quite a bit here. Okay. And so given this fact, right, that the trace of the surface in the plane z equals z naught is a circle whose radius is r of z naught and whose equation is x squared plus y squared equals r of z naught squared. All we have to do to to basically identify these surfaces is to know this equation, right? And so we could replace z naught with z, and we get the following definition. Okay, so definition. Okay, if the graph of a radius function r the function is called r, is revolved around one of the coordinate axes, one of the coordinate axes, the equation of the resulting surface of revolution, the resulting surface of revolution has one of the following forms. Okay, and the form will be almost exactly the same. It's just going to depend on which axis the radius function is being revolved around. So it'll look like this. It'll look like that if you're rotating about the, let's make that an X. If you're rotating about the Z-axis. Right, so your y squared, as x squared plus y squared equals r of z squared. This is about the z-axis, kind of like the picture we've been looking at. What if it's rotated about the x-axis? Well, then it'll be y squared plus z squared equals r of x squared. This will be about the x-axis. And then what if it's rotated about the y-axis? Well, then it's just x squared plus z squared equals r of y squared. This is about the y-axis, right? So they basically are the same form. It's just that it depends on what the axis of rotation is. Then you just kind of swap out the variables as needed there. Okay. So relatively straightforward, right? It's always basically the equation of a circle. Okay. Let's do an example here. Kind of look at an example. An equation for the surface of revolution. So an equation for the surface of revolution formed by revolving the graph then this will be y equals 1 over z about the z-axis is, well, let's write it out. So it's going to be x squared plus y squared, because we're rotating about the z-axis, x squared plus y squared equals r of z squared. R of z is just given, right? That's y equals 1 over z. So this is x squared plus y squared equals 1 over z squared. Okay. And so that means this is x squared plus y squared equals 1 over z squared, right? So in this case, this would be the graph of, this would be the equation of the graph of this guy. Okay, and so perfect. Let's do another example. One more example here. So let's say we revolve. Say we revolve the graph of 9x squared equals y cubed about the y-axis. All right, so this is some graph here in the xy plane, and we want to revolve whatever that curve looks like, whatever it looks like, we want to revolve it around the y-axis. So we want to find the equation of the resulting surface. What does that look like? Okay, maybe we'll try to draw it too. So first of all, we got to kind of figure out what we're trying to do here, right? So we've got a graph in the xy plane, and whatever that graph happens to be, we want to rotate it about the y-axis, right? So basically, we need a function. We need a radius function of y. So we need to find r of y. Right, and so all that really means here is that we want to solve for x. Right, so 9x squared equals y cubed. Solve for x. So that means x squared equals 1/9 of y cubed. And that means x is equal to 1/3 of y to the 3/2 power. Okay, so this is, so basically we now know that r of y is this. It's 1/3 y to the 3/2. Okay. So that means our equation is going to be like, it's going to look like this: x squared plus z squared equals r of y squared. So x squared plus z squared must equal 1/3 y to the 3/2, and then we got to square that. Okay, so x squared plus z squared equals 1/9 y cubed. Okay, so this would seem to be the equation of this surface of revolution. Okay, now what does this look like? Can we get a decent sketch of this? Well, so let's kind of draw in our coordinate system here. So here's z, here's y, and x is going to come out like this. X won't be as involved in this picture, but what does for example, the values of what does this look like when we plug in positive values of y? Well, basically, it's going to kind of come up like this. Okay. Now, technically, this would be in the xy plane, but I'm drawing it in the yz plane simply because it's easier in this orientation. And so you can imagine the same curve here in the xy plane, right? But it's going to kind of come up like this, right? It's basically 1/9 y cubed, right? So it's going to kind of come up like that. And when I rotate it around the y-axis like this, I'm going to get this nice big kind of like almost like a horn kind of shape. So it's going to kind of look like that. Right, so you can imagine. Right, it's got some dimensions to it. It's three-dimensional. Right, but that's more or less what it looks like. Okay. Right, and if you were to draw this, it probably, I guess, would be better to have the xy plane be more like up front. Right, the z is actually kind of the uninvolved character, right, for the sketch. But basically, you want to sketch this curve, right, which is what we've done here, except we've done it in the yz plane, but you could do it just as easily in the xy plane. And it would look the same when you rotate it anyways. So you want to sketch this curve, and then you rotate it. Right? Just imagine what it looks like when you'd rotate it around the y-axis. Does matter which axis you rotate it around, obviously. The shape will be totally different if you rotate it around the x-axis or around the z-axis. So it does make a big difference. Okay, all right. I think that is where we will end it. And so again, just an introduction to surfaces in space. We will certainly be using these as we go forward. A lot of these shapes will be using as these surfaces will be using as sort of examples, and we need functions that we can integrate. We need shapes that we can look for the area and volume of, and so these are going to serve as kind of our examples, right? We need to be able to reason about surfaces, and these are going to be kind of the examples we're going to use. So again, just an introduction. Now, next time is where we're going to actually start in on the calculus again, right? So this has all been wind up, prepping us for doing calculus in 3 dimensions. All of the vector work in particular has been preparatory, and this surface stuff is just, let's get a little bit of comfort with thinking about surfaces in 3-dimensional space. All right, so that will be it for this lecture, and we'll see you all next time. Take care.